All events just are. They're unchangeable. They're immutable. So the events can't change. And you simply, if you go back to the past, are fulfilling the precise set of events that allowed you to exist and to go on that journey in the first place.
This is StarTalk, Cosmic Queries Edition. And today we're going to be talking about time travel, inspired by Dickens' classic novel, A Christmas Carol. Chuck, love to have you on this.
Always a pleasure to be here. Although
Yeah,
I'm not
yeah.
actually here. I'm coming to you from the future. You should just know that.
Thanks for that heads up in
Yeah.
case that matters.
Let me say it to you this way. Neil, it's your kids. They're in trouble.
Thank you, Doc Brown. Realize when they went into the year 2015. Just thought I'd remind you of that.
Wow. Wow.
Yeah. We'll get back to that. So I know a little bit about time travel. I don't know nearly as much as our guest, which is why we brought him on, a good friend
Yes.
and colleague from up the street at Columbia University, Brian Greene. Brian, dude.
Our returning
doing?
champion.
Returning.
Yes.
Our returning champion, Brian Greene, ladies and gentlemen.
He's professor of physics and math. Is that right? Both of those?
Yeah, that's right. That's right.
Dang.
Right. Isn't that, wait, as a layperson, isn't that redundant?
It does sound redundant. Yeah, but I don't touch equipment. That's what it emphasizes.
Oh, yeah. It's like, get the hell out of the lab. You're one of those theorists.
Don't go near
Yes.
there.
Yeah. So Brian is a theoretical physicist and a longtime friend. And it's just a delight with best-selling books. And let me get the title correct of his latest book, because this title leaves nothing out. Here it is. Until the End of Time, Mind, Matter, and Our Search for Meaning in an Evolving Universe came out last year. Brian, that title doesn't leave anything untouched.
You need all the good search words so that you come up with anything anyone ever puts in. So yeah,
That's great.
And who's the publisher of that? We'll give them
SEO
a shout out.
optimized. Knopf.
Uh-huh.
Yeah.
Knopf, very nice, very nice. And of course, many people know of you through being co-founder, I think with your wife, is that correct, of the World Science Festival? Yeah, Tracy Day. I met Tracy Day before I knew you when she was a news reporter. Was it for NBC? Is that right?
ABC. Yeah.
ABC. Yeah. She did an interview with me.
Oh, I didn't know that.
Yeah.
She never mentioned it.
Yeah, we go way back right before. So let's put some context on the table. So Charles Dickens, which is, he wrote Oliver, he wrote A Tale of Two Cities, he wrote he wrote a bunch of stuff. And I think he wrote A Tale of Two Cities. Is that? Yeah.
Sure, of course.
And
It was the best of times.
And the worst of times. Right now, we're in the second part of that right now.
Yes, exactly. we're going to get out.
Yeah, we're
So written long time ago, 1843. And by some measures, it may be the first sort of modern literary example of time travel or the implications of time travel. Yeah. And so that's well before, like a half a century before H.G. Wells's The Time Machine. So itself quite a remarkable step to take in storytelling. So Brian, before we had Einstein's relativity, do you know, how did anybody think about time travel?
Yeah, it's a good question.
What was it missing? What, let me say that differently.
Yeah.
What do we in our enlightened modern times, with the benefit of relativity, get to say about time travel that they couldn't say before Einstein, before the 1905 special relativity paper and the 1916 general relativity?
Yeah. I look at us as the unique species on the planet that's able to lift ourselves up above the timeline and think about the past and future. So that immediately gives us at least the imaginative capacity to travel to the past and the future. But of course, you're going beyond that. You want to know about real time travel. The way that they could back then is that time is much more individualistic than anybody would have ever thought. The common view of time was it's universal. It's the same for me, for you, for anyone else, regardless of what we're doing, what we're experiencing, how we're moving.
Right.
And that Einstein shattered by showing that time elapses at different rates depending on all those qualities. How you move, the gravity you experience. That's the main new feature.
Awesome.
Interesting.
That is amazing. So now that you said that, because please, one of you, when either one of you, I'm filthy with physicists right now. I can just,
it's raining physicists.
Raining physicists. I'm an embarrassment of physicists' riches. So this is just wonderful every time I think about it. But if something is, let's go as close as geosynchronous orbit, like a satellite, and it's traveling at this speed, and they have to adjust the clocks because time is ticking differently for that thing up there than it is for us down here. And can you please just speak to that? And can you speak to, is it a literal elapse difference?
Yeah.
Like running clock, or is it something that causes it to seem like an elapse difference?
Well, I shouldn't jump in. Maybe Neil wants to take this, but it's real.
No, so why don't I'll just start with 1905 and you pick us up at 1916, okay?
Sure,
so what we learn with 1905 special relativity is that the faster you go, all right, you will perceive events around you as, well, okay. If you watch someone go fast, you will perceive their ticking clock to move more slowly than yourself. And we call this special theory of relativity because it only involved motion that did not accelerate. It was very sort of a basic case of motion. And so once you got used to that, then 10 years later, he throws in a whole other fact. And Brian, pick it up from there.
Yeah, the new fact that Neil's referring to is that gravity also affects the passage of time. So Chuck, in the example that you gave, if you have a clock on planet and a clock that's hovering above the Earth, some number of miles up there, those clocks will really tick off time at different rates because they're experiencing different forces of gravity. The stronger the pull of gravity, the slower the clock ticks. So the clock on Earth truly is ticking off time at a slower rate than the clock that's floating up there in space.
Well, so what's interesting there is that the geosynchronous satellites, because Chuck, you started this by saying they have whatever is their orbital speed, which has some significance, right? It's a few miles per second, really, and up at sort of middle. Brian, every time I talk about, there's LEO, low Earth orbit, and GEO, but middle Earth orbit, MEO. Every time I say Middle Earth, people are thinking Lord of the Rings.
Oh, don't worry, Mr. Frodo.
We've got this.
We'll get that traffic satellite fixed, sir. We'll do it.
So Brian, have you done the math yet? Since you are a professor of freaking mathematics on the geosynchronous satellites, they're moving fast relative to us, so their time we should see their time slow down, but they're farther away from Earth's gravity, so that we should see their time speed up. So there's some contest between the two.
There is, and I don't know the exact numbers in that particular case, but I do know that when they tested these ideas on a Pan Am jet in the 1970s, where they had an atomic clock that they left on the tarmac and the other they strapped into the passenger seat, maybe as first class, I don't know, on this Pan Am jet. In that particular case, it is the speeding up of time from the gravitational difference that wins out. So whenever I teach this, I'm always careful with my language because you would think that clock should tick off time more slowly because it's in motion. But when you take the competition into effect, in the end, the net change is not what you would have anticipated. But none of that really matters. What really matters is when you take all of the effects into account, motion and gravity that Einstein delineated, the prediction agrees with the observation spot on. And so these effects are truly real.
So I didn't know about that experiment. And Brian, please tell everyone.
Hateful and Keating were the two scientists.
Okay, tell everyone what Pan Am is.
Yeah.
I'm just saying.
That was the Southwest of its day, Yes.
Yeah, kids.
Pan Am actually was also the space shuttle in 2001: A Space Odyssey. It was a Pan Am space shuttle.
Oh, really?
Yeah, going up to the space station where there was an AT&T phone and a Howard Johnson's hotel.
Yeah.
Super cool. That's very cool.
So it turns out, I didn't know that about the Pan Am. That's excellent. That remains true even for the geosynchronous satellites. So the fact that they're higher above Earth wins over the fact that they're moving fast. And so when the geosynchronous satellites hand us our times to our cell phones, they have to be pre-corrected, knowing that Einstein's ideas are correct, which is just freaking mind-blowing. That Einstein could say it in his armchair, right? And it can happen in a physics paper, but to actually measure the stuff is a whole other thing.
It's totally insane. It's totally nuts. And just one other thing, Chuck, for your question, even if you take gravity out of the story,
right?
You take two clocks and you send one into space and it turns around, it comes back, and you literally compare the clocks side by side, they will show different amounts of elapsed time. So it's real. The clock on Earth in that particular case will have ticked off than the clock that went on that round trip journey. So in a sense, the person carrying the clock on the round trip journey has traveled into the future. They're seeing the Earth time than their own watch would suggest it should be.
Wow.
And one last point about Ebenezer Scrooge. He was observing different Christmases, but the big issue for any storyteller is whether you can interact either with the past or with the present that you then have access to. And so what does Einstein say about that?
Well, he doesn't say a whole lot about travel to the past, because everything that he was doing, if you actually follow it through, you can move in such a way or experience a gravitational field that allows you to go into the future. And if you're in the future, he said, sure, you interact with anything that you want to interact with. It's just that you are at a later time than your own clock would suggest. But when it comes to the past, I haven't read anything that he wrote, but it's a real conundrum that, Back to the Future popularized, right? If you go to the past, can you change things in such a way that might prevent your own birth? And then you're in a logical paradox. How could that ever happen? And people have struggled with that. And we can talk about the solutions if it's relevant to the topic here. But in one of those solutions, you can interact, but you're constrained. You don't have the freedom that you would have thought you would have had to mess things up.
Now, wait, is that constriction forced upon you? Like, for instance, if I were trying to get rid of my own self. So I'm going to commit suicide via time travel, right?
Oh, okay.
Suicide via time travel. So those constrictions, since I'm coming from a place that is already set, okay? Yeah. I go back at my origin, before my origin, I'm sorry. And then let's just say, I cause my parents to hate each other. I'm doing the reverse of the movie, right? And they end up hating each other.
Because you can do this without bloodshed, right?
Right, yeah,
you just
without
have
bloodshed.
To put your parents in an argument at a time they might have made love, and then you're not conceived in that moment.
Exactly. Or I just do something really nasty, but not, like hit on my mom, and she's just like, you are adorable. And I'm like, don't ever talk to that guy. And
stop.
So before this gets too far out of hand,
I wasn't going any further, Brian.
Slow down, Chuck. Slow down.
Let me just ask this. So would then kind of like the box of time force those events to happen anyway in a different circumstance, even though I just screwed up the circumstance under which I came into being?
No, I wouldn't frame it that way.
Okay.
The answer that I would give on that is that if you travel back to an earlier moment in time before your own birth, then you were always at that moment. There aren't two versions of a given moment in time. A moment in time A moment in time can't change because what would be the parameter through which that change would occur? It'd have to be time, but we're talking about individual moments. So if you go to the past, you were always part of that moment, and therefore you were always part of the causal chain of events that resulted in your own birth. So,
Ooh.
so you
Okay,
are
so wait. So Brian,
Damn.
Brian, in the time machine, the character has a love interest, and then she crosses the street and is hit by a horse and buggy. Back then, I guess that was a deadly thing. And then she says, "No, wait, I can fix that." He goes back in time and like prevents her from crossing the street, leaves her, and then she gets mugged and dies from a mugging. And then he prevents the mugging in a third time, and then she dies some other way. And he figures out that her death was something inherent in the timeline, and there's nothing he can do to change it.
Brian, what you're saying is what's inherent in that timeline is you. You're not an X factor. You are part of that equation all the time.
That's correct. All events just are. They're unchangeable. They're immutable. So the events can't change. And you simply, if you go back to the past, are fulfilling the precise set of events that allowed you to exist and to go on that journey in the first place. Now, look, I'm not saying this is the only resolution to these ideas, because Neil, the example that you gave brings to mind another proposal, which is this idea of a multiverse, where
okay. Well, let's pause there.
Sure.
We're going to take a quick break, and we're going to come back, and we're going to find out what kinds of time travel are theoretically allowed.
Yeah.
And I like the one where Chuck going back in time preordained the fact that he would be born, even if his intentions were otherwise nefarious or even suicidal. We'll be right back. Cosmic Queries Time Travel Edition with Brian Greene. We're back. Cosmic Queries Time Travel Edition, inspired by Charles Dickens, The Ghost of Christmas Past, Present, and Future. Brian Greene. We got the best person in the world to have this conversation with, Chuck, and you know it.
Absolutely.
So Brian, in the case where Chuck's going back in time was part of the equation that led to his birth in the first place, even if he only just realized that. Let me give an example that I've given before, but it seems to be consistent with that. Okay, so I see. So let's say we can use tachyons, which travel backwards in time, and I can send texts via tachyons. And I watch you walk down the corridor and you slip on a banana peel. And I say to myself, Brian's my friend. I don't want him to bust his ass slipping on a banana peel. I'm going to text him. So I text you via tachyons. You get the message before you slipped on the banana peel, and you look down to the message, and by looking down, you don't see the banana peel, and you slip on the banana peel. Yeah. So I ended up causing you to slip on the banana peel. Is that the same case that you just described with Chuck?
Yeah, it's a self-consistent, immutable set of events. And the text, inexplicably from your perception, is what actually causes the event that you wanted it to prevent. But it's part of that causal fabric. And that, in this approach, is the immutable quality of the timeline.
That's cool.
So it's cool. It's reverse destiny.
Well, it's timeless destiny. So all the events of reality just exist out there, and it perhaps is human perception that orders them into this causal set. But they're just all out there, just like all of space is out there. In this way of thinking about things, all of time may be out there too. And so there's nothing that can ever be changed.
Well, so in Kurt Vonnegut's Slaughterhouse-Five, that time travel scenario is what you're describing, right? And because in it, his entire time, he's picked up by aliens and he lives in a cage, all right? An alien zoo, but it doesn't matter to him because he still has access to his entire life's timeline. And when he's describing this, or they describe it to him, he said, "When will I die? You're always dying. When was I born? You're always being born. When did I go to college? You're always going to college." And so the pre-existing timeline, he could just rejoin it at any point, but the destiny is already preordained.
And there's something comforting. There's something comforting about that, right? Because even those of us who've lost parents or loved ones, in some sense, they still exist at the moment of time that they occupied. And that is an eternal, unchanging statement.
But Brian, it takes away free will.
No, it's a little fatalistic.
So yes, this is a version of negating free will, but I am one of those people who doesn't believe in any variety of free will of the traditional sort. So this doesn't run afoul of my intuition at all.
He's one of those.
Okay, Brian. Okay. See, I know we got queries.
Wait, Chuck. We got to get to questions. This is a Cosmic Queries.
Go. Get these people.
Brian, stop tempting us.
Yeah.
Brian, stop tempting us. Yeah. Shut up, Brian.
Let's act like we don't have an audience.
Brian.
Well, we do that.
Brian, stop being so damn interesting. And really let us get to our Cosmic Queries.
Man,
right,
okay. All right. Let me get to the queries. Sure. I'll put my stuff on the back burner. Here we go. Okay. Hey, this is Jay Salmon who says, or Salmon. I mean, it's Salmon, but Salmon maybe. He says, hello, Dr. Greene. Because a photon of light has no mass, theoretically, can't it travel both forward and backward in time?
Well, I love that.
Speaking of gravity, and
no, wait a minute. It moves the speed of light, and right. If time goes slower for you, the faster you go, then photons have no time at all.
Yeah, I think that's
so. If they have no time, who cares whether they move?
It doesn't make a
backwards?
Difference, right? There is no forward and backwards for photons.
So I think there's two ways of answering this question. I think both are really important. One is from our perception watching the photon. And from our perception, you fire a photon and it travels through space as time elapses. It goes forward in time. But then you say, what about from the photon's perspective? It's traveling at the speed of light. And from what Neil described earlier, when the photon looks out at the world, everything should be going infinitely slowly. And therefore, in some sense, time is stopping. Now, that's poetically fine. The problem I have with taking that too seriously is, and this may seem like a footnote, but it's not, you're ascribing some kind of experience to a photon. And a photon doesn't have experience. It doesn't have consciousness. It doesn't look out at the world, even though the poetic language is useful to invoke. And so to imagine that we could travel at the speed of light and therefore there'd be no time and time would stop is a step too far. So when we look at the photon, it's like any other particle. It travels through space, it goes forward in time. If you put yourself into the shoes of the photon, whatever that means, then poetically, yes, time would stop. There's no notion of the elapsing of time. There's no notion of aging from the photon's perspective, whatever that actually means.
But okay, so Chuck, you heard that Brian cast shade on the photon. He said it has no emotions, no feelings.
Basically, Brian thinks photons are stupid, and
okay, that's Brian.
All right, well,
Brian, all right, Brian, we know where you're coming from. All right, okay, keep going, Chuck.
Here we go. This is I like this. Let's a little more philosophical. This is Tyler J. Tyler says, how might time travel be policed or regulated if it were able to happen?
Ooh.
Yeah, because, I mean, think about it. If we could
so if you have bad actors going through, right.
Yeah. Well, again, I'm less fearful of time travel because of the view that I hold that you couldn't actually change anything. If you could, then yeah, we'd have to have the time police around here to avoid things happening that we didn't want to have happen. But
right, is that the same thing as Hawking's time travel conjecture?
Well, he's got a few conjectures, so
you think? Okay.
Depends exactly which one. But I think Hawking has said
the chronology protection
that you can't travel to the past because it keeps history safe for historians, right? Because if you could travel, you could change things, and it's also his explanation for why we're not overrun with tourists from the future. If you could travel to the past, wouldn't everybody, from the future come and visit us and be gawking at, what life was like in the 21st century? But, again, they could be here looking at us right now. Or another explanation, which is more plausible, is in almost any time travel scenario that has been dreamt up, you can never travel to a moment in time prior to the construction of the first time machine. And so if the first time machine is
Oh.
yet to be constructed, that would also explain why no one's come back here, because they can't come back here because the machine's yet to be built. So that's another very straightforward way of explaining why we're not overrun with tourists from the future.
I like that one.
Wow.
All right, Chuck, keep going. What do you have?
All right. Let's have some fun with this one. This is Kevin the Sommelier, who's
Oh, we love Kevin the Sommelier.
yeah, we love Kevin the Sommelier. Never sends us
He needs
wine.
to give wine never gives
never.
wine instructions.
Never sends us a
Advice.
bottle. Never,
Okay.
Well, no, never sends Chuck wine. Neil doesn't need any wine. I've been to Neil's cellar. He don't need no wine. Chuck needs wine.
Okay. All right.
All right. Kevin the Sommelier says, Dr. Greene, what Hollywood film depicts time travel best in your estimation? And then he says, is it frequency? I don't know why he says that, but
Well, yeah, I had a brief moment in Frequency. I tried to convince the filmmakers on how the end should be done, but it could have been more
Wait,
accurate.
Frequency is a film? I had never seen it or heard of it.
Yeah, Frequency is
That's
a
a
film.
film?
There's a time travel element where a father and a son are able to communicate across 30 years. The father's long since dead. He's a firefighter. He died in a fire. So the son tries to tell the father, go left, not right in that burning building when it happens tomorrow. And he actually saves him. So they do change the future in that particular case. So yeah, there's a multiverse way of thinking about it. But back to
They called you for advice on that?
They called me for advice, and then they asked me if I would be in it, and I'm like interviewed by Dick Cavett in 2 different time frames, and they aged me to make me look old in one, and it was the scariest thing. Really, I thought it would be so simple, but I don't know if you've ever done this, and they put the plaster on your face to mold so that they can get jowls and things on you. Feels like being buried alive. But
Excuse me, Brian. Black don't crack, so that wouldn't be necessary.
Yeah,
that's true. I'm 87. I'm 87 years old, Brian. Yeah.
Wait. So, Brian, were you in the movie? Brian, were you in the movie? I missed it.
Like
Okay,
a
I gotta
scene
go.
where I'm in a television set being interviewed in the past and another television set in the future to like set up this time warpy thing.
Oh, cool.
But I wouldn't call that the best.
Chuck, that's not his first movie. He was in the Mimsy movie. What's the name of that movie?
The Last Mimsy, yeah.
He was in the Last Mimsy.
Yeah.
Nice.
My boy was in the Last Mimsy. Interviewed as Brian Greene. We need expertise on this one. And you were great in it. You were like total natural. I loved it.
Well, thank you. I appreciate that. But to the
okay, so what's the best movie? What's the best movie?
I would say that Interstellar is probably the best one, where you have Matthew McConaughey going near a black hole, time slows down. When it goes back to the ship, the fellow left on the ship is 23 years older, even though McConaughey's only like an hour older. And then Matthew McConaughey, I can't remember his name, his character in the movie.
Just to be clear, 23 years older, not 23 years old. So the guy's gray.
Yeah. Right. Yeah. It's sort of a very crazy scene, but it's accurate. You know, you go down to near a black hole and you come back and your crew members have aged decades and you've aged an hour. But then in a very poignant moment, the character sees his own daughter much older than he is.
Right.
And she's in her bed, as you may recall, and he kind of comes into that room. So those are accurate features of Einstein's general theory of relativity.
And it's not just because you're buds with Kip Thorne, who was co-executive producer on that movie, who was professor of physics at Caltech. It's not just because you're friends with him.
That's not because I'm friends, but no doubt it was his expertise that kept the film on scientific track, which is kind of a beautiful thing.
It's a great movie.
And Chuck, did you see Interstellar?
Oh God, yes, I love it. It's one of my favorite sci-fi movies.
Did you see the name of the robot?
It's the big square robot. I forget his name.
Yeah, the big rectangular robot. It had a name.
By the way, was the best, I think, depiction of a robot in a movie. It's just a block. Like everybody wants robots. Everybody's like, I am a robot. No, it's just a block. They're like, here's a square that has appendages when it wants, and I forget its name though.
Do you remember the name of the robot?
I do not.
Brian, do you remember the name of the robot?
I'm embarrassed to say I can't even remember the robot, so I'm out of this.
Okay. The robot's name was Kip.
Kip. Oh,
yes.
There you go.
Yeah. Just thought I'd tell you. Kip Thorne.
Nice.
By the way, Kip Thorne, of course, helped pioneer LIGO, Laser Interferometry
Yeah,
Gravitational Wave Observatory, received the Nobel Prize, was the co-recipient of it a few years ago, and he did the movie. So we got some good people out there trying to raise science literacy of the world a few notches.
Yeah.
So, all right, there it goes. So good calculations there on the time. So that's just straightforward gravitational Einsteinian physics.
Yeah, that's all that is. Yeah.
That's very cool.
All right.
So
good.
So with respect, very quickly, is actually okay. Do we have any?
Wait, Chuck, are you a Patreon member? It sounds like you're asking your own question.
I paid this month.
Chuck, you a lying? That's what liars sound like.
That is exactly what liars sound like, and that is why I'm a terrible liar, because that's exactly what I sound like.
I paid this month. I paid.
Yeah. All right. So wait, very quickly. Do we have any information on the aging of cells at the speed of light, or in gravitational situations that we might be able to attribute to time travel?
Yeah, well, everything that we're talking about in terms of time slowing down or speeding up, it's truly time. So any physical process, whether it's the motion of atoms or the motion of particles in a cell or motion of aspects of proteins carrying out instructions given to them by DNA, it all happens at a rate dictated by how time elapses. So when we talk about time slowing, it's cells slowing, it's everything slowing.
Amazing.
So Brian, just to be clear, because there's a point of ambiguity here, unless we say it explicitly, it's not that being in stronger gravity has some effect on your physiology that makes you age more slowly.
Right.
It's an actual change in the ticking clock that's on your wall. That it's everything around you and has nothing to do with the effect of gravity, the strength of the gravity on your metabolism or anything. Exactly. It has to do with the space-time, the fabric of the space-time that you're embedded in. Is that a fair way to say it?
Totally fair. And so much so that even your thoughts would slow down in a gravitational field. And that's why you wouldn't even notice in your local environment that anything had changed. Right. Everything slows down, even your thoughts. So there's no obvious evidence of it. It's only when you compare time elapsing for you with time elapsing for somebody far away in a different circumstance that you recognize things have elapsed.
Now, of course, strong gravity might still kill your ass, but that has nothing to do with the time that's ticking.
That's right. That's right.
Amazing.
Okay.
Amazing. Amazing.
All right, Chuck, keep going.
Okay, here we go. This is Logan Kent. And Logan says, "Hello, beloved science professors, and happy holidays from Kansas City. I'm already giddy waiting for the episode where we get to hear about the knowledge and theories on the topic of time travel." Okay, well, we're in it.
Nice.
Okay. And he says,
and he's hailing from both Kansas cities, Casey Mo and Casey, Kansas, I guess.
Yeah, okay.
That's the plural there.
Yeah.
Right? Very good.
He says, if controlled backwards time travel was possible today, where do you think your matter or information would travel? And no, I'm not talking about what time do you want to travel, though the answers are, but rather if you were in a third-person position observing someone travel back in time, what do you think it would look like? So the time travel itself, if you were the observer, what would you see if you were able to observe the timeline itself?
So I like that, but also just slipped in there, Brian, was some mention about information.
Yes.
And that links to entropy, I presume. So if you can tackle both of those in the next 90 seconds before we go to break.
So look, I think the only real way to answer that question is to commit to a version of time travel to the past. And the version that I find most convincing involves wormholes. And the idea of a wormhole, I think many people know this idea. It's a tunnel from one location in space to another location in space, a kind of shortcut. And if you move those openings relative to each other, or you put one near a black hole, again, there'll be a time difference between the two openings. So now one opening is ahead, one opening is behind. So you go through the tunnel one direction, you go to the future, you go through the tunnel the other direction, you go to the past. So what would going to the past look like? Somebody would enter the opening of a wormhole and they would disappear and they'd pop out the other opening of the wormhole at a different place at a different time. And sure,
so in the Marvel universe, where you have Doctor Strange opening these portals, he's only moving through space. He's not actually moving through time. So that's a lost storytelling element there that they could totally do interesting things with, it seems to me.
Yeah, I mean, the richness of wormholes really arises when you have a time difference between the two openings. I mean, it's fun to have a tunnel through space, but it is mind-blowing to have a tunnel through time.
Yeah.
And also, I would add that, I think I can add correctly, Brian, that as portrayed in the movie Contact, where Jodie Foster goes through this, we presume is a wormhole, to get to visit the aliens, and then she returns. We like the idea that it's like a water slide. You know, you're in this tunnel, you're in this tube, and you're sliding in there, but it's really just a simple hole. You step through it, right? It's not some journey. Isn't that correct? Because they're basically in the same place.
They can be, but you can also have situations where the throat of the wormhole has some length to it. And then again, it would just be traveling through space. It wouldn't be some kind of, like you say, water slide or some kind of weird thing that was happening. But you're right.
Oh, okay.
So,
all right. Yep. So if you're going to do this, at least, and report on it, if you're in a wormhole and it's propped up nicely and it's safe for you, then you're just moving through space backwards in time if the opening of that wormhole is near a black hole where time is ticking more slowly than where you came from.
Or if it was there for a while. Once you set the time difference between the two openings, you can then move away from the black hole, right? Because the time difference will then persist.
Wow.
Jesus. That is... That is insane.
So, Chuck, in this one broadcast, you've mentioned God and Jesus together. This must be a very significant force operating on your brain.
Instead, I should have said, Father Time.
Why don't you give us one more question before we hit the break?
All righty, here we go. This is Jim Kelly, and Jim Kelly says, "Hi, Dr. Tyson, Dr. Greene, Dr. Comedy. Why do physicists assume that all time travelers are murderous, patricidal maniacs?" Just kidding. Just kidding. But how does a hypothetical paradox preclude the existence of time travel?
All right, let's take a quick break because I want a good answer from Brian out of that. So, Brian, we're going to discuss the paradoxes and how they're circumvented when we come back on StarTalk Cosmic Queries, Time Travel Edition, fully inspired by Charles Dickens, who kind of went there first before other novelists, thinking about the Christmas past, present, and future.
Humbug.
We're back, Cosmic Queries, Time Travel Edition, with none other than Brian Greene, whose most recent book is, I gotta read this title because it's so inclusive. Until the End of Time, Mind, Matter, and Our Search for Meaning in an Evolving Universe. And you just confessed that you put every Google search a keyword in there so that no matter what anyone is searching for in the universe, they land on your book. That's brilliant.
You've got it.
Published by Knopf in 2021. And Chuck, how do we find you on social media?
Chuck Nice Comic everywhere, people.
Nice. Leave off the everywhere, just Chuck Nice Comic.
Thank you. Yeah, you're right. Chuck Nice Comic.
And Brian,
you can find me everywhere.
Tell us about your social media footprint.
It's really only on Twitter, and it's at @bgreene. At @bgreene.
B Greene. Okay.
Nice.
You can do that.
Without a check mark, without a blue check mark.
Right. There you go.
Never had one, and now I never will, I suspect.
I heard that after Elon took over and the check mark thing, that Jesus got a blue check for paying the $8.
Yeah,
that was
finally.
one. So, Chuck, we left off with a question. Just give us the highlights of it. What was it?
There you go. Jim Kelly, who basically says this: how does a hypothetical paradox preclude the existence of time travel?
Yeah. I mean, I don't think it does. So the hypothetical paradoxes are you change the past in a way that, say, prevents your own existence. And we already discussed how maybe you can't do that. But the other idea that we made brief mention of is if instead of traveling to the past in your own universe, the laws of physics demand that you go to the past in a parallel universe. Well, if you prevent your own birth in that universe, there's no paradox. Where were you born? In a different universe. And so that's another way in which you can have the freedom to make changes to the past, but not the past of your own world, the past of.
And that's what the Marvel universe persistently does. That's how Spider-Man can have multiple origin stories, for example. We're actually accessing a different universe where similar things are happening, but not not so different that we don't recognize the story. That's crazy. So, Brian, what about information? Because information, I don't think it has mass, does it? Does it travel? Information is this intangible thing. And I always hear physicists arguing about whether we lose or gain information every time you do something with a black hole.
Yeah, I mean, I like to think of information as more concrete than that description might suggest, because information is always carried by particles. You can have an abstract measure of information, but if you want to look at the motion of information, it's got to be the motion of stuff that carries that information. And to me, that makes it much more clear what's going on. So with black holes, the whole question was, as radiation comes out of a black hole, which Stephen Hawking told us will happen, are the particles...
Instead of Louis Hawking, you mean Stephen Hawking?
That's right. They always get those confused. Different universes.
Think of specifying, Brian.
Well, there was a universe where Louis Hawking actually was responsible, but
Louis
aside. So as the radiation comes out, hey, serious guys. The question is, do the particles have a relationship among each other that carries away the information of what fell in? So it's really concrete when you think about it as information carried by stuff.
Okay, because otherwise there's no information without stuff to carry it. That's another way to say it.
It's hard to follow the information without that commitment.
So when it comes to like, for those of us who are listening that may not be so familiar with what you're talking about. So when you go into a black hole, I'm a chair, I go into a black hole. I get broken down into just particles, okay? That's all, because the gravity's so strong. Now I'm just a string of particles. I come out during the evaporation. Would I be able to be a chair again? Okay.
That is the question. That's the deep question.
Right.
And for a while, Hawking said no, that your particles would come out and they'd have no memory of their earlier configuration. The information that they carried would be lost. But he was ultimately convinced by string theorists and others that that was wrong. The particles come out and they do carry the imprint of the fact that they were once a chair. And if you measure the particles appropriately, you could reconstruct the chair when those particles come out.
Damn. That's amazing.
But the chair itself doesn't come out. You have to still make the chair. That sounds like a cop-out.
Wait, it's now an IKEA chair.
IKEA is in black holes. Chuck, I love that new theory. All right, Brian, I want a new research paper on that.
Black holes.
I want on my desk in the morning, Brian. The IKEA hypothesis.
Wow, that's amazing.
All right, Chuck, keep them coming.
Okay, let's keep it going. This is from Y Koss, and Y says, "Hello, Brian. Hello, Neil." And then he puts in parentheses with a question mark. Chuck? Okay.
That ain't right.
I don't know what's up.
We've been Lord Chuck. We've been King Chuck.
Yeah, I know.
All right.
Okay. He says, is it possible to calculate precisely where in the universe Earth was in a moment to make sure that we find ourselves on Earth's surface and not in the position that Earth was in when we are time traveling? How would you compensate for the wait, and then wait a minute now. This is when you know that Y Koss was either thinking too much or maybe might have been smoking a little something. Then he goes, Then he goes like this. How would you also compensate for the expansion of the universe when calculating that trajectory? So he's getting it all in.
He's all in.
He's all in.
So let me toss to Brian here after I say something. So in Back to the Future, they kind of avoided that problem because when Marty went back in time, he went back in time in a precise whole number of years. Okay? And so Earth would be back where it is when he goes back in time in its orbit, enough for the plot line. But if he went back a week or even an hour, he's not in that parking lot anymore at all. Mm-hmm. So Brian, tell me about all this time travel mechanisms when in fact the universe is changing. You can't just show up in the same place and expect to be home again.
Exactly right. And so when you time travel, you also need to space travel. It's really space-time travel, right? You have to pick the location in time and the location in space. And typically in these films, they only talk about the time part of things. And to make it concrete, if you're using the wormhole version of time travel, the opening of the wormhole that you're going to exit from, it's at some position in space at some moment in time when you exit. And you better be certain that you have somehow maneuvered that opening to be, say, on planet Earth, if when you exit, you want to still be on planet Earth. Otherwise, you could exit back in time, but near the Andromeda Galaxy or just an empty space. So you do need to dial both in order to get to where you are intending.
Okay, interesting. I bet they don't know that, but we accept it anyway, right? As it's implicit. It's implicit, yep. I guess, is what that is.
Mm-hmm.
Chuck, keep them coming.
All right, let's go. I want to find this young person.
The way you described that previous question, it sounds like we should have a Cosmic Queries only if the people were on weed when they wrote the question.
Oh man, let me tell you something. That's a great show.
Just legal weed, not illegal weed.
It will either be our best show or our worst show,
or the worst. No. While we're doing it, we'll think it's the best,
right?
And then afterwards, we'll know it's the worst.
Exactly, and that is kind of how that goes. All right, this is Savage 162, and Savage 162 says, "In the frontier of science, is there any idea on how to try and detect the theorized tachyon particle?" So,
remind us what a tachyon is, Brian.
Yeah, so it's what you had mentioned earlier, Neil, this idea of a particle that can go faster than the speed of light. And when a particle can go, hypothetical, I should say, a particle goes faster than the speed of light, there are observers watching that particle who will see it reach its target before it was emitted by the source. Reaches target before it was emitted by the source. So cause and effect become flipped for the observers who are witnessing the motion of a tachyon. So the question is, how would you ever detect these things? And it's a bit, first of all, to measure something going faster than the speed of light, that's actually not that hard. You start with a particle at one location and you fire it, and you simply calculate, or you measure, I should say, how long it took to get to the target. Did it beat a light beam or not? And that's it. So that's pretty straightforward. And indeed, you may recall, I don't know, some 10 years ago,
that neutrino thing.
Yeah,
in Italy, right?
Yeah, in Italy, there was a claim that these neutrinos had gone from the source to the target and beaten a beam of light. They'd gotten there earlier than a beam of light would. Now, some of us knew that could.
So, Brian, the joke about that, the Euro joke, because Europeans like joking about each other. They said that would have been the first time Italy arrived anywhere early.
Yeah, that's right. Right. That's exactly right. So that was the key tip off immediately that nothing gets. But scientifically, it would have been fascinating. It would have been fascinating. It would have been an example of something going faster than the speed of light. And so people looked really intently at the data and ultimately realized that there was some kind of loose wire or fiber optic cable or something. I can't remember the details. And when that was repaired, the particles did not go faster than the speed of light. But in principle.
But let me add, Brian, because you might not go there, and for the benefit of Chuck, that in my field, and it surely happens in your field, somebody gets a cockamamie observation, which would later be shown to be wrong. But if it's right, it's amazing. And you have these ambulance-chasing theorists coming up with an explanation of course, why that must be so. Did that happen in the case of the neutrinos?
Oh, gosh. I'm not completely sure. There must have been a few papers because nobody could have fully resisted it within the confines of the entire field. But 99% of the people who encountered that result that I spoke to were like, it can't be true. It just can't be true. And it wasn't true.
Here we go. Ryan. This is just Ryan. He's like Cher, just Ryan. He says, hello, doctors. If we developed a way to time travel backwards, could we travel to a time before the Big Bang? Or would we just break science altogether?
I love it. Brian.
Yeah, well, the whole question of before the Big Bang is a deep one. And it could simply be that there's no notion of before when it comes to the Big Bang, because the Big Bang could be the origin of time itself. And so the notion of before makes sense when you're talking about 1800s or 2000 BC or whatever. But when you get to the beginning of time itself, there's simply no conception of before. And so there may not even be a realm of reality that we could delineate as before the Big Bang.
Right. Is this the same? I think I've heard Hawking. This is Louis Hawking told me this. that going before the Big Bang might be like asking what's north of the North Pole.
North Pole. Yeah,
the
that's
whole
a good analogy.
Grid system is defined there.
Yeah.
And you can't, once you're as far north as you can go, you can't go farther north. Once you're as far back in time at the beginning, you can't go further back.
Yeah, but I should say that that's only one idea. It's an interesting and provocative one, but there are other approaches which suggest that there is a realm before the Big Bang.
Right.
Maybe many Big Bangs giving rise to many universes, and our bang may not have been in any sense the first.
Right.
And so there may be a realm.
So you'd pass through, you'd have to pass out of our sort of space-time structure and enter somebody else's space-time if you want to go before what happened with the Big Bang.
Yeah, that's right.
It's like a subway line. You reach the end of one line. I mean, you can't go any further. That's it. Yeah. But you can switch to another subway, and then you can go on from there. But you're in a different thing at that point, different train.
You're a different thing.
You do have to pay another fare in this version.
And Chuck, the laws of physics might be a little different, so that your body would fall into a pile of goo.
Yeah.
Well, that's what you get for jumping the turnstile.
Brian, just close this out if you could. What kind of time travel in all of your variants, did Charles Dickens invoke for Christmas past and future?
It sort of feels like a wormhole version where they're traveling through a wormhole to the past, and maybe they're just hovering at the edge of the wormhole, not actually entering that reality.
And therefore not interacting with it.
Yeah, therefore they're sort of more in an observer status as opposed to a participant status. It kind of resonates with that, but But don't you need a different universe now, because there were some different outcomes, right? So now you got to split. That's right. And so this would be an example where the wormhole stretches from one universe to another, as opposed to from one universe to the same universe.
Yeah, but the different outcomes were not directly attributable to the time travel. The different outcomes were because of his change of actions in the present, which affected the future.
That's right.
So the past never changed.
Yeah, I think Chuck is more current on that.
The past never changed.
Yeah.
He changed.
The past was, oh my gosh, is that what the future is going to be? No, it's not.
Right.
Because I'm going to change myself in the present.
Got it.
Right.
Yeah.
Exactly.
So the basic idea is imagine 3 or some number of tunnels emanating from this realm to these other parallel universes, sort of like slices of bread in a grand cosmic reality where each slice of bread is its own universe. You just have these tunnels connecting us to them, allowing you to witness what would happen in a world where things were different.
Wow. Mm-hmm. Damn. It's amazing.
All right. We got to land that plane right there. Brian, it's been a delight to have you back on StarTalk.
Always a pleasure.
It's really, you're just up the street. We should have you on we should be like a regular Brian feature, right? Give Brian his own minute from Brian.
I'll make it 2 minutes. Make it 2 minutes.
No, you make it whatever it's called, Brian time.
Brian time.
Near the speed of light. Brian time near
the speed of light. Oh yeah, you got it, guys. Great to have you, Chuck. Always good to have you there.
Always a pleasure
for these cosmic queries. I am Neil deGrasse Tyson, your personal astrophysicist. As always, I bid you to keep looking up.